Yeah?
What's your opinion? What do you think? How much redundant data we have in this image? Your opinion. You don't have any opinion? For entropy, you can also use maybe this. It's entropy. Probability of each symbol multiple logarithms or 2 of probability of each. Okay. Okay. What 1, 2. Okay. You can find the entropy by using this equation. Methods. And you know, to find the entropy or information contains in the image, we don't need to find the Huffman coding or something like this. Just with the probability of the each pixel, we can easily find the entropy of the image or image patch. But for finding the data redundancy and also the compression ratio, we have to use the Huffman coding, and after that we can find the data redundancy or compression ratio.
But what is entropy used for?
For the entropy, that's consists of the information in our context, like this. We talked about this. Okay. We can use this in order to find the information content in the image. For example, in this example, we found the probability of the each grade level, 21, 95, 169, and 2, and we easily find the entropy of the image by using these probability. It means that you don't need to assign some codes, for example, by using Huffman coding, and after that find the entropy. You can't find the entropy.
But for what is entropy used for? I don't understand why we should look for it.
For example, if you want to find the information, as you remember yesterday, Shahab talked about, and also you know that about the data and information that is in our image. Maybe sometimes we have lots of data, but they use just to represent a little information. For example, in this, if you consider this as an image, we have lots of redundant data here and other information in the image. It means that this data is used to represent this information. To find the information, we can use entropy. Just this. Not so complicated. Is there anyone that found how much data redundancy we have in this patch? Did anyone find it? No. Yeah. 5 more minutes. Do you know how many bits we need for the lowest probability? 4, yeah? And did you calculate the compression ratio or data redundancy?
I first find the code.
Okay, means you find this is correct that for the lowest probability we just need 4 bits in this batch. For the compression ratio and the data redundancy, you can just write like this: the probability multiple the bits that we assign to this. For example, the lowest probability have the value of the we assign 4 bits to the lowest probability. If we assign that, for example, the lowest probability is 0.04, then we assign the 4 bits to this. We can write 4 multiple 0.04. Yeah. And when we find this, we can easily find the compression ratio and the last. And you know that for the compression ratio in default, if we have the 8-bit image, we have to, for example, we have to multiply the size of the image. In this example, we have the 5 by 5 multiple 8. You have to find the for the 8-bit image, because it is the 8-bit image. Originally, it's the 8-bit image with fixed image. And you have to find this and finally find the compression ratio, and with the compression ratio you can find how much data redundancy we have in the image. Okay, let's me do it. Let's do it. Okay, for the first part of the question, we have to find the probability of the each pixel. We know that, for example, probability of the cell 110, it's 5/25. Let me check it again. 1, 2, 3, 5. 1, 2, 3.
They are fine.
It's a 5, yeah. Okay. 25, 0.2. Probability of the pixel gray level value of the 120 is 7. 25, 0.28. Okay. 140, 5/25, 0.2. 160, 4/25, 0.16. Probability of the gray level value of 170 is 3 over 25, equal to 0.12. And probability of the gray value level of 180 is equal to 1 over 25, that's equal to 0.04. And you know that if we add all these values together, finally we can get the value of the bond, because probability is between the 0 and 1. Okay, we know the probability of each gray level value or each pixel. Then we have first we have to sort them from the highest probability to the lowest one. Okay, we know that 0.28 is the highest probability value. This one is 0.2. It doesn't matter which one you use. 0.2, 0.2, 0.16, 0.12, and 0.04. And also, as you can see here, we have to add these values together. For the next step, we have to write it like this. Have the same value here, 0.28, 0.2, 0.2, 0.16, and the new value is in 0.16. Okay? Then for the next step, we know that 0.28, let's do first add these values together. This is 0.2, it means that it's more than 28. We have to put it at first. 0.32, 0.28, 0.2, and 0.2. Yeah, you know, when we add in the all steps, the probability value it has this form, from the highest probability value to the lowest probability value. When we add these probabilities together, what's the result? 0.32. Then we know that 0.32 is more than 0.28. Yeah, then we have to resort it again from the highest value to the lowest value. Okay? Then for the next step, you have to write it. If we add these probability together, 0.2, 0.2, we have the value of the 0.4. It means more than 0.32. It means that we have the 0.4 here. For this, 0.32 and 0.28. Okay? And again, we add, if you add these probabilities together, we can find the value of the 0.6. Yeah, 0.6 and 0.4. Okay? Then finally we have two probability values. We have to assign the code to which one. We know that we will, in this step, we assign just 1 bit. The highest value will give the value of the 0, and the lowest value will give the value of the 1. And we have to back to the first step, and we know that when we have the value of the 0 is 0.4. when we have the probability value of the 0.4, we assign the one value here, means we have one bit, and when you know that 0.6 is after the combination these probabilities, it means that we have to write the first values here, and then add one more bit to this. It means that for the first one 0, and for the second one 1. It means that in this step we assign the 2 bits to this value and 1 bit to this probability. Okay, we can come to.
Sorry, but I didn't understand that.
You know, for the 0.6 we assign the value of the 0. Yes? Okay. What's the 0.6? 0.6 is a combination of the 0.32 and 0.28. Yes? It means that we have to put 0 for both of them. That's the value of the 0.6. Then, in this step, we know that we have to assign one more bit to each one. Then, we assign for these two, that's the combination of, this value is the combination of these two. We have to assign 0 to the highest probability value and 1 to the lowest probability value. Okay? And we know that in this step we assign 1 bit to the highest value, and for the rest we have to assign 2 bits. Okay? We come back to the third step. We know that for the value of the 0.32 we assign these bits. Okay? We directly can write it here, and for the value of the 0.28 we also can write it here. Okay? For the value of the 0.4, we know that the 0.4 is a combination, after the combination of these two probability, it means we have to put 1 for each one, because the value of the 0.4 is 1. Then after that we have to add.
Because 0.2 are the same value, right? That's
Yeah,
one
but it doesn't matter. We know that, for example, this 0.2 is for this and this 0.2 is for this. But when we write it in this form, it doesn't matter that you for example, you put it here or you put it here. It doesn't matter. But in the sort, we can assign one more bit to this. It means that 1 0 here, 1 1 here. When we have the same value, it doesn't matter which one is at the first.
But how you distinguish them? Why we cannot put the same value to them? 1 0 1 0 to both of them?
What?
I mean, but why don't put the same values? 1 0 and 1 0?
No. For each probability, okay, we have to assign when this is a combination of the two probability. For each one, we have to assign one more bits. You can, for example, if we consider, for example, this and this, okay, it doesn't matter that we put the 0.2 here, or this, or here, or put this here. What's the difference between them? Nothing. It means that we can easily sort it in that way that we like, and after that, according to the highest to the lowest, we have to assign the value to them.
Why do we have to assign 1 bit for each of them?
Because, for example, for this probability, we know that it's not just one value, it's the two values. Okay? It means that when for the two values we have the one more bits instead of the one value here. It's the reason that when we back to the this step, or for example to the rest, we have to add one more bit to them. And because we have one value here, but it's a combination of the two values, then we have to add one bit to save the values. Also similar to this, 1 for this, 0 1 excuse me, for this, 1 0 for this, and 1, 1 for this. Also, we know that for this, we have these values, okay? Also, 0, 0. And also, we know that we have to add one more bits to this. We can write 0 and 1. As when we come to the first step, we know that for the first value, we have the 2 bits. We have to send 2 bits, 2 bits, 2 bits, 3 bits.
Which one we can use? Because we have two codes for.
We know that this value is a combination of these two values because we have the flash. Okay, it means that at the second step it's fixed. Then we have to put it here. But for this, we can add one more bit. 0 and 1. It means that for the lowest probability, we assign 4 bits. For the highest probability, in this example, we assign just 2 bits. But for example, in that example, you see that for the highest probability, that is 0.4, we just assign 1 values or 1 bits to the code. And for the length of the values, we can write average is equal to, know that the 0.28 multiplied by 2 plus 0.2 multiplied by 2 plus 0 multiplied by 2, 0.2 multiplied by 2 plus 0.16 multiplied by 3 bits plus 0.12 multiplied by 4 plus 0.04 multiplied by also 4. The result is something like this. 2.48 bit symbol. Okay? I think we have a mistake here. We have for the find the compression ratio, we have to put the original one here. 5 by 5 by 8. Okay, sorry for my run. Okay, to find the compression ratio, we have to write this. Compression ratio is equal to 5 multiply 5 multiply 8. And for the compressed image, we know the length is 2.48 instead of 8 feet here. It means that we have to write 5 multiply 5 multiply 2.48. Okay? The result is 3.2258. Okay? And for the data redundancy, if you want to know that how much data is redundant in our image, we have to use this equation. This is the compression ratio that we have here. R is equal to 1 minus 1 over 3.2258 is equal to 0.96. That's, we can say that we have 96% data redundancy. we have 96% data redundancy in our image. And also we know that this rate means that we just have 4% information, 4% information in our image. And also for the entropy, you can write this 0.4 0.04 logarithms are 2 of 0.0204, excuse me, plus 0.12 multiply logarithms of 0.12 plus 0.16 logarithm of 0.16 plus 0.2 logarithm of 0.2 also 0.2 logarithm of 0.2 plus 0.28 multiply logarithm of 0.28. And finally we can find the value of 2.188 bit, the unit is bit per pixel. Then we easily find we compress the image in this form by using the Huffman code. We found the compression ratio, that is 3.2258. We found the amount of data redundant in our image, that is 0.96 or 96% data redundant we have in our image. And also for the information, we know that for each pixel 2.4188 bit we use in this image. And that's it for today. Do you have any question?
How we can interpret this entropy? Like, what does it mean 2.41?
It means that for each pixel of our image, we have to assign the 2.41 bits. It's the average of our coding or image. It means that for each pixel in that, for example, in that image patch, we have 2.41 bits.
An average for each pixel?
Yes.
So
No. Bit. The unit is bit per pixel.
bit per pixel, but then what is 2.48? It's bit per...
Bit per symbol. Symbol, that is the value of each pixel.
Okay.
So you might not have all of the values inside of your pixel, inside of your image.
Yeah.
You might only have like a few grayscale limits there.
Okay.
So that's how many bytes.
But the
per
compression ratio is very...
The compression ratio is 3.22. We have the compression ratio here
Yeah.
because
it is
the
96
original.
So it is compressed by 96%. I mean, it's,
No.
it's reduced the size
Yeah,
by 4%. Yes.
It means that we compress the image 3 times.
Okay.
It means that the result is 3 times smaller than the original one. Okay. Then, if we want to find the redundancy data redundancy or redundancy data in our image, we can't use this, and by this value we know that in the original image we have the 96% of data redundancy.
Okay.
And it means that we remove this value in the compressed image. means that we just use 40% of the data in the original image to represent the compressed image. And we lost 96% of the data in our image. It means that we don't need them to represent the image or compressed image.
So we lose 4% of the image.
We just use, yes, 4% of the data to represent that amount of information that we want to put in the compressed image.
And is it done automatically, or we have to do it manually? All of these operations. This Kaufman decoding, we have to do manually, yes?
In your exam, yes, you have to do.
But
in the MATLAB there is a function for this, or I think also in the OpenCV that
We
you
use
can.
MATLAB in the exam.
No.
But will you upload this to the Moodle, maybe, or should
What?
will you upload this to the Moodle, or we should take a picture?
The video of the last lecture is uploaded, yes, but I will upload it today or tomorrow. Yeah,
But
it's recorded right now.
is it visible?
It's kind of feasible, yes.
What?
The exam, is it open book or not?
What?
The exam, is it open book or not?
I think it's the open page. I don't know what's the. I think I remember the last year you can bring 2 pages or something like this for your final exam.
Shahab said that you can use all the physical material you can.
Yeah, okay. If he said it, so it means that it's open. But
You
not
can
open.
print it.
The BPP is
Bit per
Okay.
pixel.
Will we give the questions for the
You asked him. You asked from him. I don't know exactly. I'll see you. Write the question for the final exam. But I'm sure that one of the questions is from the convolution or correlation that I showed one example for the sharpening or the smoothing. One of the questions is from the color image. For example, convert the HSI to RGB or RGB to HSI. One of the questions is the Huffman coding. One of the questions will be with high priority. I don't know, this year Shah will ask you about the Fourier transform or not, but maybe one of them will be asked for the Fourier transform. It means that we have the image in the time domain and we need it in the frequency domain. It means that you need to use some Fourier transform equation. I don't know this, he will ask it this year, but I remember 2 years before he asked a question like this. But although you know the 3, already you know the 3 questions of the final exam. No, one is the correlation and one is the correlation that you have to use some mask in order to smoothing and sharpening. I solve one example. One of the question is the convert the color spaces, for example HSI to RGB or RGB to HSI, and also showed an example around 2 weeks ago. And also one of the questions will be something like this. It's the prepared question.
So you're printing out no
No, just you have to write the rest.
All the questions are right, like norms, theoretical, we can this exercise.
Yeah, it's exactly like this. That you don't need to calculate anything on MATLAB or something like this.
Sorry.
Yeah.
Could you estimate when the first homeworks will be evaluated?
I evaluated the first and second homework for the people that was in the class 2 weeks ago, 1 week ago on the Tuesday, but for the